yesterday we mentioned there's a pulley, ball bearing, and the other one I forget. Okay, this is ball bearing. Okay, so what's going on for ball bearing? What's happening is when you have various kinds of ball bearings. This is the roller type. So roller bearing. So the roller either it's rotation is following like along the central axis or having a tilting angle. So when it's tilted, it provides some kind of support in both axial direction and also radial direction. So usually when the roller is tilted, it provides a stronger support. And of course, if you want to uh, manufacture the components for tilted bearing, it's more complex, so the price could be higher. Or I forgot to talk about ball bearing. So, or inside there are multiple metal balls, and uh, being placed surrounding the entire ring. Okay, so you have a single ball or double ball, okay? Or you can even have more rows of those balls. Okay? So when when you if you think about the shaft problem, so here's our shaft, okay? And here's the bearing, okay? So in fact, there's a metal ball inside, and there's an inner ring and outer ring. Okay, inner ring, outer ring. And remember, when we do various kinds of analysis, we usually say, oh, there's a reaction force. And maybe it's carrying some load right here on the shaft. So for simple cases, usually the force comes from the side of the bearing. But sometimes you also have reaction forces along this direction. So it's like this is, you may have some other geometry here. So maybe there's a force pushing the shaft toward left. So there is actually some reaction forces from the outer geometry pushing it back, right? So the force is pushing here from right to left, and the support is pushing left to right. So sometimes the geometry inside carries loads along the axial direction as well. But for the usual case, when you design for a shaft, most of the time you are preparing for loads along this radial direction. If you need to carry loads along this axial direction, you may need the roller bearing, because some rollers are designed for carrying loads along this radial direction. But how do we design it? The load distribution inside the bearing is very complex. There's no exact analytical model for it. It's too complex. So they realize you can use a statistical approach to study for the relationship between how much load you apply and how much cycle this bearing can last, like the life. So force and life. So for bearing, basically cycles. And also another thing would be reliability. So reliability right here means after a certain amount of cycles, how many will last. Okay? So these two are very related. Okay? And here's our equation. So F represents the load, L represents the life. So from here you can see there's a model FL 1 over A, the power of 1 over A equals to a constant. So they found out, they have done experiments, they realized, hey, when you take logarithm, uh, so if I say this constant is C, okay, and if I uh, if I try to make a drawing for the relationship between F and L, then I can put L to the right hand side. So F equals to some constant times L to the power of A, right? And if I take logarithm, log F equals to, so this will be a constant. So log C plus A log L. Okay? So what does this mean? This is like a function y equals to a. This is like a variable x plus b. So it's a linear equation, right? Y equals to ax plus b. Because the c is a constant. Log c is also a constant. So that's why in this log plot, it's a linear curve. So they have done research and realized, okay, uh, for most of the bearing, um, the relationship uh, between the force and the life follows this trend. So they build this model, and the experiment shows that it's matching pretty well. For most of the ball bearing, this power A, this coefficient A equals to 3. For roller, sorry, A equals to 10 over. So this is like a recommended power. If you are working on some ball bearing from some category, you need to check what's the coefficient right there. Maybe different manufacturer produce different bearings, and their relationship between the force and life follows different coefficients. Okay, so if we have this relationship, what we can do is we now realize we can use it to estimate the life of the bearing when it's carrying certain amount of load. Since we have that relationship, FL 1 over A equals to constant. So it's like you can have a condition 1 and life 1, and this must equals to the same equation at condition 2. Okay, that's why you have the equation on the top. And the textbook or category usually would like to give you some numbers. It's called C10. So this will equals to some value called C10. And let's just say L. Okay, 1 over A. So what is C10? So it's like actually for this L there is a specific L. It's 10 to the power of 6 usually. 1 over 8. So what's going on? What is C10? So C10 is like if you apply the load of C10, if the unit is Newton, okay, and then operate the bearing or the rotate the, maybe just say rotate for 10 to the power 6 cycles, okay, then gravity equals to 90%, which means 10% of failure rate. So the 10 represents failure rate, 10%. Okay, so if you have 1,000 pieces, all of them apply the load of C10. And all of them rotate for 10 to the power of 6 cycles. 100, so 10% would be 100. 100 pieces will fail. That's the rating. So it's a rating, load rating. Okay. So before this lecture, if you have never designed for bearing, you have never heard of how to design for bearing, here's something you should know. Because when you buy the bearing from the category, it tells you C10. And he may not explain what C10 means. So from the usually, let me show you something. I hope he has. Okay. Here. So like this is ball bearing, right? Different dimensions. Inner diameter, outer diameter. This is like how thick, the width, how wide the bearing is, and this is like the round, the fillet at the corner, and I forget what is shoulder diameter. Or shoulder. Shoulder diameter is right here. shoulders. So it's like you have the inner diameter, outer diameter. You also have like if you need to know this geometry, then it tells you what is the shoulder. Okay. So get back to the table, and then the most important thing is C10. Or even C0. So C0 is like zero failure rate. So it's like a 99.999, a lot of 90% of success. So it's like if you apply, depends on different kinds of content. Let's say this deep group content, basically how you design the holder for the bearing. So if you apply 2.24 K Newton, or if you apply for 5.07 K Newton, and then rotate for 10 to the power of 6 cycles, 10% fails for this case. Almost no bearing fails for this case. Okay, so from this category, then you know, depends on how you expect this bearing to last its life. Then you know how much, what's the allowable force that should be applied to the bearing. Okay. Another thing I would like to share with you is this particular drawing. So if you now have this relationship, the log-log diagram, we already showed it's a linear curve. And this is the C10 that you get from the category. And right here, basically, this is basically log life, right? So this is x10 would be log. I'm not sure. I think it's the log with e. So log to the 10 to the power of 6. So this is 6. Okay. Actually, that x10 is 6. So it ends up with some point right here, and then this line represents reliability of 90% because this comes from load of C10 cycles of 10 to the power of 6, and on this particular line, you will be matching this linear relationship, the log-log linear relationship. So if you use this equation, this set of equations to look for allowable force for longer life. So for example, if you are looking for, this is longer life, right? Same reliability. Then the allowable force would be smaller because you want longer cycle. Or if you are looking for higher loads, then with the same amount of reliability, you can only last for a shorter life. Okay? Now, how about the curve for different reliability? So, if you study from the curve, horizontal line of C10, what's happening is on the horizontal line, this is a log. Actually, it's a log. This log life, and this is for C10. Okay, and if you study for reliability, up to 6, which means life equals to 10 to the power of 6, you got 90% of 90% of reliability. Okay. So how about the reliability when you have fewer amount of cycles? So you usually have a much higher reliability. So this is like 100% right here if you don't have any cycle. And if this reliability usually drops. Okay? When you have, if you apply the force of C10 and you start to count how many failure rate you have to compute for the reliability. So as the life, the cycles increases, reliability gradually drops. So from 100% to 90%, this should be a statistical model. Statistical model. Okay? So in this textbook, I think it's showing some model called Weibull. They use Weibull model. This is gamma function. Here, this is called Weibull distribution. So I'm teaching another course about system reliability. We talk about Weibull. So it's an exponential model, and I'm not spending a lot of time on this. I'm just telling you there will be nonlinear equations to describe how this drops. So if one day you are designing for different levels of reliability, you can plug into, for example, this is a waveform model, or some other models. As long as that reliability trend fits to the experimental data. If you're designed for higher reliability, for example, 95%, so you will know, oh, you will have a shorter life. If you still apply C10 and you are expecting for 95%. So maybe this curve is represent 95% of success rate. So from here you can see, if you apply C10, when you go move up to here, you have shorter life because you are looking for higher uh, reliability. And once you find this point, this line is valid. You can also you can still use this linear relationship. You can use it to design for specific point with specific reliability. So force, life, and reliability, all three are tightly related in this particular drawing. So this is actually a three-dimensional plot. There are three parameters: force, life, and reliability. These are like contours. You get different contours. So as this contour goes this way, reliability becomes higher. As this contour goes that way, reliability goes low. Do you see it? Okay. And the way this drops can be described by the waveform. Okay. So that would be what I want to cover for that ball bearing, very quickly. Do you have questions? So in the future, when you design for bearing, you don't just design for the dimension. You also need to know how much cycles you can still be functional, and you should know how much load it can carry. So that's bearing. Talk about pull. Oh, clutch. Then let's talk about pull. So in the design for pulley and the belt, the issue is you need to know the length of the belt. So there's usually a geometrical calculation about the estimated length of the belt. So when you purchase a belt, you know the length. Or if you already have purchased some belt with certain length, then you can use it to design for the distance between two pulleys. Basically, over here, the distance C. Okay, and you can have different ways to install the belt. Then geometrically, the length of the belt would be calculated in a different way. It's just geometry, so I'm not going to cover how to compute them. Uh, so you can even have a flat belt, and then you have a twist at along the way, so you can change the orientation of the pulley. Okay, so that's another interesting setup. Also, you can use variations of the diameter of the pulley to change the speed, okay? Just like your bicycle. So what's important about the belt is to study the force inside the belt. So why is it important? Because the tension on both sides of the belt is different. And it is because when you have different tension on both sides, so there is a delta F, like a force difference. And because of the force difference, you can generate torque. Okay, if the tension on both sides is the same, then you cannot have, because torque equals to the delta F times velocity, no, times radius. So uh, you need the difference of the force. So now, how do we know the difference of the tension force on both sides? Is gonna use a calculus. So if you pay attention to a part of the belt, right here, you assume uh, the right hand side is having a tension F1, and the other side is have the same tension but with some increment of the tension force. So here's the pulley. Here is somewhere you have contact with the pulley. So it's like you are starting somewhere here. It's like you are starting somewhere here. You just pay attention to a small portion. Once you can do that, all you need to do is to do integral along the all for the entire area which you have contact between the belt and pulley. Okay? So let's now pay attention to a small cut of the belt. Now you have some tension on one side, some increment of the tension on the other side, and because this material is rotating is in high speed, so there is a centrifugal force going outward, and since you have tension of the belt pushing, like pulling the belt, so the belt is like being pushed down toward the pulley. So the pulley will have a reaction force pushing the belt outward. So you have normal force. Okay? And because of the normal force, so there would be a friction force in between. It depends on which direction your belt is rotating, the friction either goes this way or that way. Okay? So that explains all the forces. So all you need to do next is to do balance of force and balance of moment. So not going through everything, just by balance of forces and also some general equations of the centrifugal force. So at the end, at the end, it ends up with a equality equation with small deltas. Delta n, dn, small increment of the normal force, small increment of the theta, small increment of the centrifugal force. There's a equation like that. And then this is continue to do some derivation. So this is the final equation, right? F is going to be a function of beta, because from the drawing you can see that as you investigate different positions of the belt, the tension at that particular point is gonna change. So if let's say theta right here is 0, then your F equals to some the tension on the right edge. So it's like if you have belt like this, and maybe here is theta equals to 0. So let's say you have tension 1 here. So if you're starting for the F right at the 0 angle position, F equals to T1. But as you move on to specific points, maybe theta equals to 30 degrees, then the force right here would be T1 plus something. And that, whatever increment, is actually a function of theta. Depends on theta. So that's why F is a function of theta. And based on the derivation that earlier, I'm not going through the detail, it ends up with a derivative of F with respect to theta minus friction coefficient times F equals to some constant. So this is a friction coefficient, and this is like a mass per length. This is the radius of the pulley, and this is the angular velocity. So they are considered as constant when you are starting for specific problem. So it turns out it's like a problem or you can write it like this. It's a differential equation. Okay? So if you have a differential equation, you can solve it like how you do it in the engineering math. Right? So at the end, using using what you have learned in engineering mathematics, at the end you can compute, you can determine the F1 and F2. So basically, the force, you can compute for the force everywhere. So over here, I think this is the final equation. So you can see this F equals to some constant that I mentioned earlier. These are the constant that I mentioned. And here's the variable at different angle. You have different force, and this will be the force on one of the edge. Okay? And you can also use it to compute for F1. If you know F2, you can compute for F1 when you plug in the angle. So in this particular set of symbols, F equals to F2 when theta equals to 0. Let's write here. F at theta equals to 0, it's a number F2. Okay? And let's say this is a pulley. Okay? So from here, this is theta equals to 0, and here is theta equals to phi. So right here, this is F2, and here is F1. Okay, so when F equals theta equals to phi, F equals to F1. And F1 and F2 are different. You can use F1 to minus F2 to get the delta F. When you have delta F, you can use it to compute for power. So let me just show you how to compute for power. Okay. Power equals to delta F times velocity. Okay. So then you know what's the required motor power to drive the belt. Okay. So I think there for the pulley section, there are many equations. I think it's quite interesting to see differential equation in design of mechanical components. So in the future, if you are interested, you can always Google ChatGPT for design for pulley and belt. You will definitely see these set of equations. Try to derive it by yourself, and then in the future, when you design for your belt, you will have proper decision of the belt. Okay, so unfortunately, I cannot cover the other one. I cannot cover the clutch and brake. Clutch and brake also requires some calculus, some integrals. So you may, if you're interested, you can Google for it. Okay. So I think that's what I want to cover today, and let me double check with the calendar before you go. Yeah, so next week, progress, discussion, and some Dr. Patel will share some of his experience of industry robots, and then final presentation. So you have 2 weeks to prepare for it. Okay? Any questions? So if no questions, I guess that's the end of all my lectures for this semester. I hope you have learned something. I have teaching videos online. If you in the future, if you are looking for solutions, you forget about something, you can go to take a look at those videos or just internet. Internet are better than us. Okay, that's it. Thank you. Please make sure you do the roll call. If you have questions, you can come.